Gottfried Wilhelm von Leibniz is known for being the last universal genius known to man. The German prodigy made significant contributions to the fields of mathematics, physics, technology, logic, medicine, theology, linguistics, philosophy, history, law, politics, and so much more. Today, we will focus on Leibniz's contributions to the STEM fields. Leibniz was born on June 21st, 1646 in Leipzig, Germany, 2 years prior to the end of the 30 Years' War, which had ravaged Central Europe. His father, Friedrich Leibniz, was a jurist and professor of moral philosophy at the University of Leipzig, who died when Leibniz was only 6. Growing up without his father, Leibniz had to teach himself independently. He did so by studying the extensive content in his father's library. Using these resources, Leibniz had become fluent in both Latin and Greek. As a childhood prodigy, Leibniz entered the University of Leipzig at the shocking young age of 14. In the University of Leipzig, Leibniz studied philosophy, mathematics, and law. After receiving his degree in 1666, Leibniz applied for a doctorate in law, but was rejected because of his young age. This caused him to banish his hometown forever and enroll for his doctorate at the University of Altdorf. As soon as he graduated, he was offered a professorship at Altdorf. Leibniz declined this offer. Instead, he studied mathematics, geometry, and physics in Paris. In 1676, Leibniz became a librarian in Hanover, where he was given a lot of leisure time, which he used to conduct more mathematical research. 8 years later, he published the first official document on calculus. Leibniz also discovered many new inventions and wrote numerous documents, which gave him a spot in the prestigious Royal Society. Leibniz also helped design new types of hydraulic presses, windmills, lamps, submarines, clocks, carriages, water pumps, and a calculating machine, which used the binary system he invented himself. STEM contributions. The most important contribution Leibniz made to the STEM fields was the invention of calculus. The second most important contribution Leibniz made was the discovery of binary. This is because we need binary to run our computers and electronic devices. Newton discovered calculus using a geometric approach when working on his theory of fluxions. His theory consists of fundamentals of instantaneous change, which is a basic component of calculus. Newton discovered calculus on his own in order to help him describe the celestial motions of the planets in our solar system. But the actual term calculus was introduced by Leibniz some years later, when he published the first theorem of calculus. Contrary to Newton, Leibniz used more of an analytical approach when discovering calculus. Therefore, it is unreasonable to claim that Leibniz plagiarized Newton's work. Their different approaches suggest that their discoveries were simultaneous but independent. In addition to Leibniz's development of calculus, he also created a mathematical notation to be used in modern-day calculus. Leibniz did this by adapting the integral symbol of summa, which is Latin for the sum or total of. This integral symbol is more used in today's calculus than Newton's notation, which was a small vertical bar above the variable. In 1684, Leibniz published the first fundamental paper on calculus. His paper on calculus was called A New Method for Maxima and Minima, as well as Tangents, which is not obstructed by fractional or irrational quantities. This theory revealed how to find the area under a curve. This means the area of the section in between a function and the x-axis. Leibniz was able to find the precise area by finding the limit of the infinitely thin rectangles, as you can see over here on the graph to the right. This is also known as infinitesimal calculus. There are two different branches of calculus. One is derivatives and the other is integrals. Derivatives are used to find the instantaneous rate of change, and integrals are used to find the area under a curve. Gottfried Leibniz systematized infinitesimal quantities and introduced the calculus notation that is used today. Leibniz's new infinitesimal calculus allows us to precisely analyze functions within their continuous domains. In Leibniz's theorem, the derivative of capital F is lowercase f. The antiderivative is vice versa, which is what we use in integral calculus. This theorem, we use the differential and integral calculus together by clearly stating how to find the area under a curve by using anti-differentiation. Leibniz's notation. Y equal x is used to denote a function. In this case, f of x represents y. dy over dx is what is used to denote the derivative of a function. And summa y dx is what is used to denote an antiderivative of a function, also known as an integral. Summa is the notation Leibniz invented. This represents all of the antiderivatives. The development and use of calculus has had wide-reaching effects on all areas of modern living. It underlies nearly all of the sciences, especially physics. Virtually all modern developments, such as building techniques, aviation, and other technologies, make use of calculus. Many algebraic formulas are now used for ballistics, heating, and cooling, and other practical sciences were solved using calculus. Calculus has been used in a broad field of subjects, including all the STEM fields and some forms of economics. Calculus is extremely important in our lives, since it is the mathematical system used by scientists, engineers, and medical researchers. These are the vital workers that are needed to develop our infrastructure, discover new medicine and treatments, and further our general knowledge of the universe. One example of calculus being used in everyday life is when engineers are creating architecture. An architect engineer uses this calculus tool of integration in determining the amount of necessary materials used to construct curved shapes. An example of this would be the dome over a sports arena. Calculus is also used to measure the rate of that structure. Medical scientists use calculus to determine the growth rate of bacteria. They could use this information to find out what medicines they need to provide to stop unwanted bacterial growth. Most importantly of all, calculus has been used in many of the most important recent scientific discoveries. These include Einstein's theory of general relativity and George Maxwell's theory of electromagnetism. These scientists used calculus to explain the great logic behind their wonderful discoveries. The success of calculus has been extended over time to differential equations, vector calculus, calculus of variations, complex analysis, and differential topology. It took 100 years, however, before calculus was to be made rigorous. Mathematicians named Cauchy, Weierstrass, and Riemann reformulated calculus in terms of limits rather than infinitesimals. Therefore, the need for the infinitely small, non-existent quantities were removed and replaced by the notion of quantities being close to each other. Both the integral and derivative were reformulated in the terms of limits. These rigorous justifications of computations is an important development to the field. By applying more logic to calculus, mathematicians are now better able to understand and extend the field of calculus, as well to come to terms with some of the more subtle aspects of this theory. The modern binary number system was invented by Gottfried Leibniz in 17th century in his article Explication de l'arithmétique binaire. Excuse me for my French. Leibniz's systems used a base 2 system that counted only zeros and ones, unlike our base 10 system we use to count from 1 to 9. Because of the ability of binary to be represented by two phases, on and off, it would later become the foundation of all modern computer systems. Leibniz's documentation was essential in the development of this process. Leibniz used his discovery of binary as the basis for his invention of a calculating machine. This machine was capable of multiplying, dividing, and even extracting roots. This was the precursor to the modern-day calculators. Binary numbers are the foundation for how computers work. In computer systems, the binary numbers are known as bits and can be used to encode images, make calculations, and encrypt digital messages. For example, a digital image is encoded through a dedicated line of binary. If this image is displayed on a screen using a 16-bit code, we can expect the outcome of more than 65,000 pixels, since the base of 2 to the power of 16 is equal to 65,000. Each pixel in this image is given instructions in terms of binary, determining which color is to be best shown on the pixel. For calculations, the computer uses Boolean algebra, which uses binary. Machines also make use of binary when they add numbers by flipping switches. This means the switches could only be in the state of on and off, and there is no intermediate state. This increases the reliability of computers and eliminates the chances of any exceptions since there is no intermediate state. Binary numbers found their use later in George Boole's algebra. The Boolean algebra found its use in the early 20th century when a student named Claude Shannon from Massachusetts Institute of Technology realized that Boolean algebra defines the working of electric circuits through multiple logic states, like and, or, and not. Since then, Boolean algebra, which is fundamentally based on binary numbers, is used in the logical analysis of electric switches and transistors, which are mainly used in the computers and smart electric appliances today. These binary numbers turn on and off electric switches inside the mechanisms, helping it to do its function it was programmed to do. Leibniz argued against prevailing ideas at the time held by Newton, which included the conception of time and space in absolute terms. This is because Leibniz wrote, quote, "I have said more than once that I hold space to be something merely relative," end quote. Leibniz's belief in relativity in space was eventually proven by Einstein. Coincidentally, Einstein used Leibniz's calculus to find his equation, which proves special relativity. In conclusion, Leibniz is one of the most important thinkers of the 17th century. In our physics and mathematics classes, Leibniz is often unfairly overcast with Newton's shadow. We must remember Leibniz for his heavy influence his work has had on the progress of the STEM fields to this day.